and how those relate to each other. For example, how do you go from normal to log normal? That's very simple. You put a log on it, but you can go to chi-squared, and that has a link with the gamma distribution and the like. So this is a pretty cool resource if you're interested in understanding the relationship between the different distributions that people use. So probability. Now, the key things to know, we try to summarize here, and I think Mark did a great job of really focusing on what matters. Obviously, some rule. If I'm looking at the probability of X, I can basically evaluate this if I have a joint distribution P of XY by integrating over Y. This is if I'm focused on X in particular. P of X and P of Y, so Px of Y is the joint probability distribution. So it's like, what's the probability that X is here and Y is here? This is in the case of both being discrete, for example, or what's the density function of these two being at a certain point if you are in continuous space. And then, of course, you can use those to build up the marginal probability distributions. So integrate over Y to get P of X, or integrate over X to get P of Y. The interesting one, though, is the conditional probability. It's like, if I have information about X, what does it imply for Y? And this is pretty interesting and worth an example. So let's say that you have here 2 cartons. One of them has 2 bananas and 3 apples, and the other one has 4 bananas and 1 apple. In each case, like 5 items in each carton. You pulled up, in this particular case, a banana, and you're trying to say, hey, Y is a banana, so what does that tell me about the probability, for example, that I am in carton 1. Carton 1 is the one with 2 bananas, and carton 2 has 4 bananas. So you're trying to really use the new information that you're being given to have a better update about what you think. So to start with, the 2 cartons look the same. So probability is half. Like, don't have any specific information about one or the other. So, to start with, and this is what we call a prior distribution. These terms are important because you'll see that they come up all the time in, the literature. Prior, posterior. So what do we mean by that? Prior means this is a priori, like before I start, my best guess about, what's going on, which is here that, it could be carton 1 or carton 2 because, they look the same. I have no particular knowledge. So now we're going to start doing some calculations. We know that the probability of getting a banana if it was carton 1 is basically 2/5 because we have 5 items and we have 2 bananas. Same thing with the second one. It has 4, so it's a higher probability. We call this the likelihood. So this allows us to calculate what is a banana. Remember, we said we can integrate, over X to decide what's the probability of Y. This is exactly what we do here. We say, what's the probability of a banana? It's the probability of having a banana if I was in the first case, plus the probability of having a banana if I was in the second case. So it adds up to 3/5. So now the question is, how can I use this to decide what's my probability that I was actually pulling from the first carton? And this is the conditional probability that we care about. So Bayes' theorem says that you can do this, and that what we call the posterior distribution is basically the product of likelihood times prior divided by evidence. And so if I do the calculation here, that says that, the probability that we are with the first carton is basically, probability of banana, given that I'm in carton 1, times probability of carton 1 divided by total probability of banana. And this is how the math works. So I'm listing here some, existing ways to describe this. So there's prior belief, there's posterior belief after you went through this, and you use things like likelihood and marginal likelihood. But I wanna give you some intuition about what's going on, because Bayes' theorem is actually very important. For me personally, it's actually the most important theorem in science. Can somebody tell me why this would be? Why is Bayes' theorem so important? Anybody? Yes? Any sense of, why this is stupid-looking formula is so important? I'll tell you, because it's the foundation of all science. Science is basically observing facts and determining from the facts you observe what's going on and what's your model of the world. Let me give you an example. If you look at physics, like, we had Newton with classical mechanics. Newton, understood gravity, and classical mechanics was so good that you could literally, predict when events would happen, when the moon would be a certain position, when planets would visit Earth, sometimes like, many decades ahead of time. And, it was incredibly powerful. However, classical mechanics is actually wrong. And Einstein, when he came with relativity, the general relativity, proved that actually it's a good approximation of what we think is reality now, which is, general relativity for astronomy. And so he made a few experiences about, the way the light bends that actually proved that, classical mechanics was wrong. And to this day, we have never found a way to say, general relativity is actually wrong on anything. So what I'm saying is, it's by observing that you build up better knowledge about the world. And when you think about deeply, like, how do you incorporate, like, new knowledge into the world? Well, it's Bayes' theorem. Okay, so now there's a formula in Bayes' theorem. And sometimes, when you're not familiar with this, it's very easy to get kind of like unclear about what the terms are, etc. And, So I'll tell you, in my point of view, what's the easiest way to understand Bayes' theorem. So imagine you have two events, A and B. A is the hypothesis. In the case of cartons, like, are we in carton 1? This is what we want to know. B is the measurement or the observation, okay? So if you think about, this is the whole world, the ellipse around all this. There's a certain part which is A, there's a certain part which is B, and of course the intersection is A inter B. So what are we trying to see here? We're trying to evaluate probability of A. So follow me closely here. Probability of A, if anything, if you had no knowledge about the world, is literally this surface divided by the whole universe surface. That is probability of A. Is everybody with me so far? Okay, makes sense. Now, something happened. We observed B, okay? So the whole world is not this big thing. We know we are in B now because we observed B. You're with me? So what's the probability of A? Probability of A is happening while we are in B. So it's probability of intersection of A and B divided by P of B. You see? Which is here. So if you're not sure about Bayes' theorem, just draw a few circles and you'll be sure to get it right. And by the way, this shows you also the symmetry, because you can do it in one side and you can switch also to calculate on the other side. So that gives you a sense of how you can easily compute. And that's the idea of, like, general knowledge. First, all the potential assumptions were here. With observation, we narrowed down. Without classical mechanics was true, but it turned out it's not true, and general relativity is true. Until now, we will never be able to prove general relativity is true. We can only prove that it's false if we find, an observation that says it's false. So there's a little idea about Bayes' theorem. So let's talk differentiation now. So this is a pretty important concept, as you know, because, you could say that modern machine learning is in many ways all about computing gradients faster and better, etc. So the idea is, I have data. Here I have n pairs, xy and yi, which are, the dots on this figure. And I'm trying to fit a functional around those. I'm trying to find a way, if you want, to explain the empirical data that I'm seeing. So literally, learning is like finding a model, which is a functional f, which, kind of passes very near, ideally on all points, but that's not realistic, kind of passes nearby. So f of xi should be ideally not very far from yi. That's a general idea. So if I take a polynomial, for example, of, the degree d or order d, so what I'm trying to do is, which I can write as theta transpose times x. So theta are the parameters of the polynomial, so they are the coefficients of the polynomial, and x is the observable. I'm trying to find a set of parameters, theta star, like a good set of parameters, such that I'm not far from what I'm trying to predict. Okay? Everybody with me so far? Easy? Cool. So to do that, I can say, I want to be close, so let me score the error I'm using. And typically in machine learning, we very often use, the squared loss. And we'll discuss later during the presentation of why this is important. But the idea is here, okay, so I'm going to define this L theta function, L being the loss. It depends on theta, and which is literally the sum of the differences squared. And I'm trying to find a minimum for theta. So that's what I'm trying to do here. So let's look at this in the context of a neural network, for example. So imagine that your inputs are x, and you have 2 dimensions, so x is in R2, and the output is y in R3. What I'm doing here, I'm doing a matrix multiplication, adding coefficients b as bias, and adding a nonlinear, functional such as sigma. Like here, sigma would be sigmoid, for example, but it could be something else. So this is how I can represent this. So my parameters in this particular case are a and b. And you could say that, y is f of a and b of x. So that's how we look at it. So a few points here. I mean, this is just to refresh everybody, But matrix multiplication is not commutative. And if you look at basically the collab that was built, you can find examples of this. So here we're going to be operating in multiplication space. Some things remain, but some other things disappear. Importantly, when you multiply matrix, it's very important that those nearby dimensions are the same. So you cannot multiply a matrix if, for example, this one here was different from this one. So the k's here have to be the same. And if that happens, they disappear, and you multiply a by b. A is n by k, and b is k by m. You get c, which is n by m. Everybody with me so far? Cool. So in NumPy, this is how this would look like. And in particular, you can write it as n sum, where you're summing literally the terms here at the bottom. So we're going to try to find a set of parameters such that the fit is good. And this is literally, how supervised learning works and many other types of machine learning models. I'm just trying to find the right parameters, A star and B star. And for that, I'm going to need to differentiate my loss by the coefficients. So that's what we care about. So let's look at what's going on here. If basically my functional was just one parameter into one parameter, this would be classical differentiation. Multivariate is saying, hey, my input now is a vector. It has a dimension n, but the output is still, a real number. Where things get interesting is when you have vector fields. So I'm going from an n-dimensional vector into an m-dimensional. And actually, and this is what we're going to deep dive today, you can also do that with matrices. So you could have a functional that takes you from an m by n matrix into a p by q matrix. And this is where it gets exciting, because most of you are saying like, yeah, I know all this thing. Well, why am I here? But trust me, by the end, you'll find some stuff which is interesting. So general rules of derivation, differentiation. So it's additive. So the derivative of the sum is the sum of the derivative. The product rule is, if I have a product, it's actually the sum of differentiation times the other terms both ways. And importantly, the chain rule, and this is the one which is important in machine learning, which is to say, if I compose functions, the derivative of the, g of f is actually the product of f prime here times g prime of f. It's a product, and this will be very important actually in the context of machine learning and matrix multiplication. And quotient rule, which we're adding here, but you could see actually quotient rule as just another case of the product rule, or actually, the chain rule. Like you could say g of 1 divided by g is the composition of g times the inverse. So all this makes sense, and you've seen this before. And of course, how do we define derivative is like, what happens if I slightly perturbate my functional f around the point x. So I add a little h, and I see kind of like the rate of increase, which is of course the tangent. So it's pretty obvious when you have limited dimensions, but it gets more interesting afterwards. listed here a few examples, which are classic. Hyperbolic tangent, for example, the derivative is 1 minus the square of hyperbolic tangent, log of x, derivative 1 of x, etc., etc. So let's do a few examples. So let's try to say that I have a function g of z, where g of z is 6z plus 3, and z is, a function of x, actually, which is minus 2x plus 5. So my question for you guys is, what is g of f prime of x? So you're allowed to talk to speak to your neighbors. I'd like you to figure out what it is. Just in question, right? Like back to basics. So does anyone have an idea? And is courageous enough to talk? We've listed the formula on the top, yeah? So what do you guys think? Any luck? Anyone? So maybe let's start with, f prime of x. What is f prime of x? Minus 2. Yes, it is minus 2. And what is g prime of z? What is it? 6. Okay. So we have minus 2 and we have 6. So what do we do in the chain rule? We multiply. Okay. And yes, that's what we do. We multiply. So you see, it's very important to get practice on these kind of things because, when you practice, it's not as obvious. So there is one which is more advanced, which is to say, hey, g is a hyperbolic tangent and z is x to the power n. So if you haven't seen the slide when I moved, what do you think it is? Again, it's the product of derivatives. So what would it be? What is the derivative of f? Yes, n to the x power n minus 1. And what is the derivative of g? 1 minus tangent square. So that's what you have there. So you see, it's easy if you know what is going on. So far it's not very difficult. So where things get interesting, obviously, is in machine learning we have multiple parameters, multiple variables. So in this particular case, let's look at a case where we have n dimensions into the input and only 1 dimension to the output, which is r. So partial derivative is basically exactly like before, but I'm perturbating just, if I'm looking for the partial derivative to xy, I'm just perturbating this particular guy, and that's it, okay? So that's all what I'm doing. So by doing that, obviously, I can perturbate in n different dimensions. So the output is basically a vector, which we call the gradient or the Jacobian. We write it 1 to the n. That's how we write it. So it is basically a row vector. And this is something that we'll discuss a little bit, but a good rule of thumb about how these things work is if f is of dimension 1, okay, that's the output, and the input is in dimension n, it should look like the output times the input. This is very important. So input is n, and output is 1, so it's 1 by n. This is a good one to remember, because it will be interesting when things get more complicated. So let's do some partial derivatives. If you look at the first one, f of x1, x2 is, this formula, x1 square, x2 plus x1, x2 to the power 3. What is the derivative to x1? Yes, anyone wants to say? So I differentiate to add versus x1 to start. So the first term, what's the differentiation to x1? Yeah, 2x1, x2. And the second one? Yeah, it's x2 to the power 3 because it's x1 that's moving. Yeah, that's correct. So we just did this one. And you can do the same with the differential versus x2. So if we look now on the more advanced case, what would be on the right the differential versus x1? What is it? Yeah, go ahead. What do you think it is? 2, yeah? Yeah, it's 2 to the x1 plus 2 x2, 3. Because it's the idea that it's a square, and I'm compounding, and differentiating into the square. And if you do the same for x2, you get 6x squared. So the goal of this session is really to refresh you. So I encourage you to try to do these by yourselves, because sometimes it can be a bit rusty. But then if I write those in vector shape, this is a R1/2 vector, and that's how it would look like in this particular case. Make sense? Everybody with me? So this is the case where I have basically a functional that takes me from 2 dimensions into 1 dimension. Okay. And of course, all classical rules apply. So it's the same spirit, and you can see that we've used them. So now we're going to look into a more interesting case. So remember that we're trying to minimize losses, and losses are expressed as an error squared. So let's call this error E. And here, basically, you're trying to minimize half of, E squared in vectorial space, which you can write E transpose E with a factor half. So my question to you is, we're going to try to compute dl by dx. So what's going on here? X is a variable with n dimension. It's the input here. We multiply it by a matrix A, which is m times n, so it works because it will work on X. So E and Y, the results are in m-dimensional space. So my question to you is, what's the dimension of dl by dx? Because this is where it gets interesting, right? So dl by dx, what could it be? Any sense? Anybody wants to try? Yes, you said what? She said m's time n. Actually, it's actually over there, 1 to the n. Because the way you need to look at this is, what's the dimension of x? What is x dimension? N. And what's the output? L, it's a loss. So dimension 1. So this is very important here. So the result is dimension 1, and the input is n. So this is a key trick here. It's very important to remember that, because when things get hairy, it's very good to have a mnemonic that you are sure works. So the output, like the size of the gradient, is basically the target dimension, in this particular case dimension 1, because it's a loss, and times the dimension of the output, that is n, okay? And if we look at how we get there, actually it's the chain rule. To differentiate dl by dx, I differentiate dl by de, and then de by dx. So we're gonna do this one together. So what's going on here? dl by de, what is e? It's an error term, but I'm differentiating directly on this one. We said E is basically the sum of, the single components of the E vector. So it's going to be half of E1 square plus half of E2 square, etc., etc. So if you do the differentiation, first it's going to get into a 1 by m vector, because E has m dimensions. But importantly, if you do the math, if I differentiate 1 divided by 2 of one of the components E square, I get E itself. So it's exactly E transpose. And when I differentiate E by X, what's going on here? Let's try to see what's going on. What's the dimension of E? Dimension of E? M, right? What's the dimension of X? N. So the dimension of d divided by dx should be r m to the n. Everybody with me? You see, it's actually pretty simple if you focus the right way. So, and if you do the math, and we will do it in a bit, you'll see that this works. So, interestingly, the result can be actually written as E transpose times minus A, and you can check the dimensions work. And you can also write it in terms of the error itself, because E is Y minus AX, remember? So that's what we have. So to summarize what's going on, we have a vector Y in m dimensions. We have a vector X in n dimensions. So if I write what that means, and this is also another trick, is like when you're not sure what's going on, write it component by component so that you get a sense. So Y1, what does it depend on? It depends on all the x's through its own function f1, which is, you know, basically a scalar. And same thing until ym, which depends on fm of x1, xn. Everybody with me? Yeah. So now, if I do the matrix, as we said earlier, it's a m by n, and that makes full sense because the first one, y1 divided by dx, it has n dependencies, which are here. And you do that for every component here, which is its own function. And so it's normal that you should summarize everything with a matrix, okay? So you see that this actually makes sense. So if I want to compute, in this particular case, let's say f of x is matrix A times vector x, the differentiation, if I want to differentiate that, could you tell me what's the dimension of df by dx? Let's apply the rule. What should it be? What's the dimension of f? F is how many dimensions? M dimensions. And x is? So what's the output? M times n. Yes, and that is correct. Good. Okay, so you're following. And if I'm looking now at exactly what are these terms, so if I write this as a sum here, a11 x1 plus a12 x2, etc. So that's the matrix product in detail. You can see that for colon fi, it's the sum, the term fi, it's the sum of the aij xj, and where the sum is on j. So when I differentiate this versus xj, I get exactly aij. So the result is basically that the differential is exactly the matrix. And so in a sense, everything works the way it should be. Because when I look at f of x, there are two things I need to know if I'm going to compute the gradient, is what's the dimension of that gradient, but then intuitively, well, I'm trying to perturbate x, and A is telling me how this perturbation happens. So it kind of makes sense if you look at it from a pure scalar point of view that it should be A. So it's kind of like the intuition that you have on scalar actually holds in matricial, if that makes sense. See? So the key thing is just to check the dimensions. And we, of course, have chain rule. So let's do an exercise with the chain rule. So imagine in this particular case that I'm going from R2 to R. So my function f takes an input of dimension 2 and gives a scalar. But this, this function this input x, which has 2 dimensions, actually depends on 1 dimension, which is t. So we're saying f of x is this, and x to the t is actually, x depends on t with, this sine, cosine formulation. So the question is, what's the dimension of df by dx? So can somebody tell me the dimension of df by dx? try to apply the rule we said about input and output. What should it be? Sorry? What's the dimension of f? 1, yes, good. What's the dimension of x? 2. So what's the dimension of df by dx? 1 times 2, exactly. That's the correct answer. And dx by dt is the other way around, 2 by 1, because I'm literally, x here is the output is 2, and t is the input, and t is input 1. So dx by dt, it makes sense that it is output times output, which is 2 to the value of 1. So you see, these things make sense once you figured out how the rules of the game, you know. Because if you don't, it can be very tricky. So now the question is, what's the gradient df by dt? So the question is, like, can you work out what this gradient is, basically? And obviously, we're saying here it's the chain rule. So df by dt is basically df by dx times dx by dt. So what does it look like? Try to write it down on a paper. Yeah. So we said there are two terms, right? So we can try df by dx. So df by dx, we said it's a 1 times 2, so it's a row vector. But what is it? What is this vector, df by dx? So I'm going to differentiate versus the first term, so which is versus x1. So when I differentiate versus x1, what is it? Yes, 2x1. And when I differentiate versus x2, 2. Okay, so it's basically 2x1 and then 2 as a row vector. Yeah, make sense? Good. So now what about dx by dt, which is the other way around? It's a column vector, and it's a 2 by 1. So what is it? Well, basically it's like I take the component and I differentiate by t. So what are this differentiation? What's the derivative of sinus? Okay, and what's the derivative of cosinus? Minus sinus, yes. And basically this is exactly what's going on, you see? This is 2x, which we wrote sine of t, and 2, and the other one. And it just makes sense, and you can see that the dimensions work, so you get to the result. So you see, like, this is really cool to practice a little bit. It gets you going. So we don't have too much time, so we'll skip the break. And you know, as a counterpart, you will have a larger break at the end of the session. So let's get to the next dimension, and this is really like next dimension. So remember, we said that, you know, the key thing to remember is it's the output has the derivative has a form which is target dimensions times you know, input dimension. So obviously we saw this in the case where I have a d-dimensional into a e. But where it gets really interesting is that it actually generalizes to cases where the input and the output are matrices. So imagine that my input is a m by n matrix and the output is a p by q matrix. It still works. So if I apply the same rule, df by dx here, and those are all matrices, is in R p by q, which is the target, which is the output, times the input, which is m by n, okay? And that's what we call a tensor. So hey, now you understand why we talk about TensorFlow, you know. TensorFlow is this idea that I'm gonna do derivative in all those dimensions. And this is exactly what you guys are gonna do now, so stay with me. But importantly, this has meaning in real world. So can somebody imagine what does this mean? Can somebody give me an example of machine learning where I have an m by n input matrix and I have a, you know, p by q output matrix, and this is kind of like not a math exercise but actually something useful? Can somebody give me an example? What could this be? you know. Try to give me an example of, you know, potential thing it could be. I'll give you a hint. One of my first slides, as an example, it was about what? Yes, image classification. Yes, or yeah, classification. Or let's say visual AI. Okay, okay. So now let's narrow down. You know, like Bayes' theorem. You know, there was the whole world. Now we're talking visual AI. So how could I do an application which is useful with a shape like this? So the input is P by Q. So let's say the input is an image. So literally those are the pixels of the image, okay? And what is the output? P by Q, what is it? It's another image, basically. So what would be this other image, for example? It could be an image where you have done, for example, segmentation in that particular image. So in each new pixel of the new image, there is some information which would be like segmentation, like classification at this exact pixel. Okay? Everybody with me? So this is actually really useful. This is actually really what's going on, you know. And importantly, you can see that the derivative, and this is, I'm trying to give you an intuition about what's going on here. You know, and this is not just a math exercise. The intuition is that I'm going from an image P by Q to another image, maybe like a scaled down or something, or the same, could be the same as well, M by N, yeah, the other way around, sorry. We're going to M by N into P by Q, okay? So if you think about it, what we are saying is every pixel in the new image has potential dependencies to all the inputs in the initial image. So this sounds very fancy, but it's just a way of saying every pixel in my new image, you know, obviously could depend on all the pixels of the initial image. Okay, make sense? So that would make sense then to say, how does each one of those pixels in the new image depend on everything in the new image? So the dependency is complex. The dependency is basically, you know, depending on m of n times n. It's like it depends on each new pixel. And I do this, of course, for all the pixels of the new image. And indeed, this is the right dimension. Did you get does that make sense to you? You see, so this is exactly, basically what we need. So let's try to do the math here now. So now, in this particular case, we are doing a function f equals ax. This is actually a case we've seen before. And we saw basically that if my dependency is on a matrix, the shape is going to be 1 times n times m. Yeah, here the output is only dimension 1. The input is m times n. So basically this is saying, hey, I'm looking at one pixel. This pixel depends on all the pixels of the input image, which was m by n. Everybody with me? So, and it works like you expect it to be. So there's no surprise here. So we're going to deal now into the details of how does this work here. So remember, now we're differentiating towards A, you know. Previously, we differentiated towards X, and we said, hey, the output is basically A. Here, when I differentiate versus A itself, every functional here has this 1 divided by m divided. So if my output is in m dimension, it is m output times m by n input, okay? So how does this look like? So if I do the calculation, you know, this is literally y equals ax, but I'm writing it down. So if I ask you on the I row here, what is d of fi divided by aiq? So remember, there's ai1, x1, ai2, x2, and so on and so forth. So aiq, what should be the derivative? If I differentiate, it's like saying, what's the dependency to aiq here? It's not difficult. Yeah, go ahead. Yeah? What is it, you think? Let's make it more simple. Like, let's say Q equals 2, okay? So we are literally looking at this term, AI2, X2. And I'm differentiating versus AI2. So what is this derivative? X2, here we go. And if I do this for Q, it's XQ. So when you're not sure, you see, like when I asked you the first time, nobody answered. And the second time, everybody answered. Well, you're not sure, make it more real. Let's say Q equals 2. Yeah, I decided that. See what happens, you know? And that's basically what happens. So now imagine I'm doing this for the whole line. What should it be? As a vector. It should be X, and X transpose, because remember here where it's a row vector and X was, you know, column to start with. Make sense? And what about, I'm trying to differentiate this I line versus the AM, for example, parameters, or the A1 parameters. What happens? Is there any dependency? No, there is none, so it's 0, indeed. So basically, well, we're pretty much there. We basically, if I summarize this in, you know, like in total format, we are saying that the line Fi, the row Fi, has a dependency on the whole matrix A, which is really only the, you know, X coefficient, but positioned at the ith line, and 0 otherwise. And you can see that it's the right dimension. Make sense? So you can see that how you can compose these things and grow. And this is like a great explanation from Mark, who built those slides, is, you know, like what am I trying to do here? I have a matrix A, and I have dependencies with X in R3. So I'm literally differentiating versus X1, get a matrix, because each component could have a dependency to X1. Same thing with X2, X3, and the result, as we said, if A is 4 by 2, and the output is, you know, in the input is 3, it's 4 by 2 times 3. So everything makes sense. You could reshape this also and saying instead of a 4 by 2 matrix, I'm doing an 8 by 1, and then I differentiate and reshape. This is typically what you would do in, you know, computing packages sometimes also. So this is just to give you a sense. So let's get back to neural networks now. So neural networks, I'm doing a matrix multiplication of my inputs X. Imagine those are the pixels in the image. And I'm multiplying them by matrix A. And I'm adding a bias B, and I'm calling this fancy new vector Z. And in literature, typically Z would be called, you know, logits or logits, depending on how you pronounce that. And you add, of course, a non-linearity, which is a sigma, which could be a sigmoid, which could be ReLU, could be LU, could be a new one you invented, as long as it's non-linear. Okay, so that's my formulation. So what's going on here? My output is dimension M. We are in R to the power M. And so is basically Z, because here I'm just doing a hyperbolic tangent, which is the non-linearity here. So Z is in R to the power M. And of course, X is n-dimensional, and A, given that it has to do AX to get you to Z, is M by N. Okay, everybody with me? So this is really what happens in a neural network on one layer. And of course, after that, we're gonna compose. So let's try to figure out what's going on here. So if I tell you df divided df to the db, so what is the dimension of this? Can somebody tell me the dimension of this? df by db. What did we say? We said it was outputs times inputs. What's the dimension of output? M, okay. And what's the dimension of the input? M, okay. So here we go. It's an M by M matrix. Magic, right? And if you do, the way to calculate this is you would actually do it by chain rule. You would do a df by dz, and then a dz sensitivity to db, okay? And you can see that here it's an m by m by m by m, so this collapses into a m by m. So everything is exactly the way it should be. Okay, so what about df by dA now? What's the dimension? What's the output dimension? M, it hasn't changed. But now the input dimension has changed. What is it? M by n. And indeed, it's m times m by n. Okay. So you see, it's simple, right? But yeah, if I asked you this when you arrived, I guess you wouldn't have necessarily figured it out. Okay. So, and again, chain rule, df by dz, and then you differentiate z versus its matrix component. So if I do that, what's happening actually? So let's differentiate df by dz. So f, remember, is m dimension, which is a hyperbolic tangent of z. So its input is z, which is m dimension. So if I do that, well, it's really like the differential of hyperbolic tangent component by component. And of course, it only works when, like, if you have the first one, which is hyperbolic tangent of z1, it's only going to have a dependency to z1 itself, and zero otherwise on all the other z's, and so on and so forth. This is why there is a diagonal term. So, you see? And if you're not sure, you can write it down, and you'll see that it works pretty much perfectly. Okay, so this is df by dz. But the fun, if I look at dz dB, basically it's the identity, because just, you know, it's just a linear relationship between them without any coefficient change. You know, like the ax doesn't matter here because we're differentiating versus b, so it's of course identity. Cool. But the fun is on dz by dA, because dz by dA, remember, this is a m vector, which I'm differentiating versus an m by n. So the result is actually m times m by n. And if you work out the math, it's a little bit like what we saw before. You're going to get all the x coefficients. Okay? So basically, we've built up everything we need. The Colab example that we will be sharing with you has all this, and it's written down explicitly. I think it's very important, even though modern software packages give you access and compute all those derivatives automatically. I think it's really important to do it once yourself, to actually write a backpropagation yourself, to really figure out what are the dependencies. But so, you know, we're pretty much getting close. So let's examine a real case where I have data y, and I have x inputs, and you know, y is in m dimension, and x is in n dimension. So this could be you're trying to predict some features of customers or something like that. But of course, there is a noise term which is here represented by epsilon, and epsilon is normally distributed here with variance sigma. So I'm trying to use my neural network, exactly the one we saw before, where I do ax plus b, elevate that to the, you know, compose with the hyperbolic tangent. So I'm trying to figure out which coefficients would reduce the loss. Remember, I'm trying to get my formulation here, the link between x and y. I want to make them f of x as close as possible to y. Of course, there is noise and there is reality, so you're never going to be able to fit this perfectly, but you want to minimize that, and your degrees of freedom are really A star and B stars, the coefficients of the neural network. So how could we do this? Well, basically everything we've seen before is going to be useful, because the dependency of the loss to the matrix, you can, by chain rule, say that it's the dependency to the error, and the error itself depends on f, and f depends on z, and ultimately z depends on a. So everything we've done before actually applies, and in the Colab example, you can actually do the whole calculation and get to the outcome. So you see, so in a sense, really, like, machine learning is a very powerful user of matrix multiplication. And of course, what's the intuition behind this is, if I'm looking at the loss, ideally I'm trying to find a global minimum. if I can find that, but more realistically, maybe like a very good local minimum. But I'm moving by gradient descent, so I'm trying to go towards the steepest descent. The gradient is telling me which way I should go, and I'm going in that direction. So, you know, you can do this in one dimension, and it's pretty clear what's happening here, and you guys know this anyway. And I keep doing this until it converges to hopefully a reasonable result in terms of parameters. So in the real world, though, we don't do one-layer networks. Why, by the way? Why don't we do one-layer networks and make them very big? Could be, yeah. I could say, why don't I do one layer and have 1 million parameters? Yeah. Go ahead. Yes? Nonlinearity? But you could do a nonlinearity here. I could put a hyperbolic tangent or a sigmoid. Why don't we do just one layer? Keep it simple. Computation? Yeah, but there is an argument which is it's not really computation. It's really like, what can I get with one layer versus what I would get with multiple layers? What's the advantage of multiple layers, intuitively? Yes? You could extract more features. It's like there is more abstraction potential. Because multiple layers is saying, really, I'm taking the output here of layer 1 with parameters A0, B0, and then I'm reusing that. So remember my first example where I'm going into visual AI classification from simple pixels to a very complex concept such as a car or a specific person. It's going to be, this is happening in part because you are using base level results, like recognizing, like if I want to simplify this, in reality it's more complex than that, but say, maybe in one layer I can recognize edges. In the next one, 2 edges make a corner. Multiple corner with certain shapes could be a human face. So it's this idea of compositionality, which is very important. This has been actually studied empirically. And we basically, we realized that, up to a point, adding a few more layers allows you to get, better results up to a certain point. There is a trade-off, of course, but one layer doesn't work. And, you need at least, several layers to, in practice, get good results. But it's this idea that I can reuse results and keep building, because one layer has only so much expressibility, if you want. And these are complex features. A human face is a complex feature, basically. Okay, so we're trying to train a multi-layer neural network, okay? So I'm literally starting with F0, which is X itself, and I compose by Fi every time. So we're gonna try to find the right parameters such that now the parameters are not just matrix and bias for one layer, it's for all layers. So I'm going to try to, basically, on all this jungle of parameters, try to find a good example. So basically, find the matrices of coefficients AK, the biases BK for every layer K from the beginning to the top. So how do I do that? I start from the top. So on the top, if I look at the loss itself, the loss itself comes from a functional Fk, which is driven by the parameters AK-1 and BK-1. So basically, I'm doing a chain rule here. I say dl by Fk, dfk by theta k, which is exactly what we did for one layer. So that gives me the dependency to the theta k-1 parameters. But obviously, there is more than that. There's dependency on all other previous parameters. And the magic here is that I can keep going. What's the dependency on k-2 layer? Is to say, I'm not, I started here, but here I continue. There's a Fk-1, and now I find my dependency to theta, basically the matrix k-2 and b to the k-2. And I keep doing that. And of course, I'm storing the results as I go. So this is basically how, you compute by backprop. You start from the end, and you keep going, and you're going to have all the coefficients. So essentially, that is really what's going on. And once you have all those coefficients, you can tweak them a little bit in the direction of steepest descent. with your favorite, like gradient optimizer, which here is just you doing like simple gradient descent, but there are variations. But you get the sense of what's going on. And every layer, the matrix calculations in every layer are exactly the way we saw them. We just keep composing. So one way to look at it is I keep multiplying matrices all the time. This is why in modern machine learning there is such, like literally like billion-dollar bets on how I can calculate matrices faster from both software point of view, like improving the algorithms, but importantly even from a hardware point of view. For example, companies such as GraphCore, NVIDIA, Intel, others, they are all fighting how do I do my matrix calculation faster. And it's kind of funny that a concept which at the end of the day is not so fancy has become such a huge deal because it makes a difference. If on your smartphone you can do 15 billion calculations on a matrix multiplication style in, I think the fastest now, the latest result from Google AI model which is optimized for mobile was like 5 to 10 milliseconds with really amazing results in terms of accuracy if you're looking at ImageNet and stuff. Not the best that you would get with a massive model, but really so close to it, which is impressive. So really we're in a period of exponential progress, but yet it's very important to understand the basics. So very briefly, why squared loss? We all decided arbitrarily that it was less loss squared. We could have said, it could be norm L1, why L2, or why not L3 or something else. Well, so the reason for that comes from the concept of log likelihood. So I'm quickly going to dive into this. So if you express your functional with theta parameters, and you say, why is it f to the x plus normally distributed noise, if I take the log probability of this, I can maximize log likelihood, okay? So what does it mean, maximizing log likelihood? It means that, I am gonna try to find the parameters, theta, such that what I have observed would have been quite likely, or maximum likely, given what has happened. So if I do this, basically, so here, I have a y, and I'm saying that, the dependency is f theta the x plus a normally distributed noise, which is to say I'm trying to basically fit the parameters theta such that my observed y is not far from the mean of the distribution, which is f theta of x that corresponds, okay? And there is, of course, n log to 2 pi, that's the square root of 2 pi, but it really doesn't matter because what I'm gonna do here is I'm gonna differentiate versus theta. So it doesn't matter, the first term is a constant, it doesn't matter. And, I'm trying to maximize the log likelihood, which is the equivalent of saying I'm trying to minimize the minus log. So if I look at this formula here, it's a square. So the key point here, the key point to remember is by using L2 norm in the formulation of my loss, I'm doing the equivalent of trying to find basically maximum likelihood parameters. And that's powerful because that means that you are on a solid theoretical foundation and that if you do things right under certain suitable probability, conditions, you will converge, okay? So the reason why we use L2 is for the fundamental link in a normally distributed multivariate format, the link to basically maximum likelihood. And by the way, why this square here is because the distribution of normal variable, there is the minus a half of e to the minus half x square. So that's the square, And e, it's the error, so it's y minus f of x. So everything makes sense, if you want, from that point of view. And of course, you have tons of problems to deal with, which are basically like making sure you're not overfitting, because if you keep doing that without any kind of control, you're gonna just memorize the particular data set, and you're gonna be bad on like held out test set or things like that. But you're familiar with this. So to summarize, and I hope I didn't kill you to start with all those matrices and math and stuff. At the end of the day, I think I think it's important to keep things simple. So the takeaway from this session is basically, as we said, L2 square has a fundamental, strong theoretical foundation due to its link with maximum likelihood under normally multivariate distribution. That's a key one to remember. The other key one to remember is when you're doing differentiation in fancy matrices and stuff, as we said, it's output dimension times input dimension. And if you're not sure, and there are y's and j's and k and l and m going in every dimension, write it down on a paper or use it on a collab where you're actually doing it for 1 or 2 coefficients, and usually things should be very clear. And in matrix in general, it's an extension of the differentiation that you have for scalar, except that some properties are lost, like it's non-commutative and things like that. But still, y equals ax, differentiate by x, you get I, So it's not crazy, but this gives you a sense basically of what you need. And I think if you survived this lecture, you have more than enough to have a great indaba. Here we've listed some references, and this is these great references from Mark. And in particular, Mark's book. Mark, is your book out? Okay, so the PDF is available, so I strongly encourage you to have a look, because credit to him, the slides and the clear mathematical description is to Mark. I'm just the messenger here, and I hope that you had a great time. And importantly, this is meant as a refresher. You should feel solid about all those. And of course, we will share the slides and share the collab, and we should be good. Yes, the slides are going to be on Slack. That's perfect. Okay. And thanks a lot. Have a great Indaba. It's amazing to be here. The weather is great. So let's have some fun and let's learn some cool stuff. Thanks a lot.